All right, folks, how's it going? For those who haven't had me yet in studio, this is Paul coming to you live or actually recorded from my basement. I don't have anything as cool as Jeff's Greyhounds down here, if you've watched some of Jeff's walkthrough videos, but this place is taken over by my children's toys. So you may be seeing those from time to time. All right, today in class, we're going to be sort of wrapping up the Duckies module and shifting gears to our last module this semester, Robo Ninja Warrior. So we're going to get a chance to sort of map out the concepts and key ideas that we learned in this mini module that culminated with the Ducky on a ramp problem. And then we're going to launch into some new content on robots. All right, so I'm going to guide you all through some of the exercises today. So to get started, I'm going to go ahead and share my screen and show you the day document. All right, so here's the document for today. So like I said, we're going to start out looking at these amazing ducks and seeing what those equilibrium angles looked like and debriefing on that. And then we're going to go into Robo Ninja Warrior. So Robo Ninja Warrior is a module based around the idea of understanding how you can program robots to solve tasks autonomously. So we have a bunch of different challenges that your robot will face. They will start out simple and get more challenging as we go. Along the way, you'll be learning a lot of math, physics, and engineering content. So while we are teaching robotics algorithms and techniques that you would do in a robotics course, the focus here is primarily on learning the mathematics and algorithms that sort of lie beneath the surface and sort of support those types of tasks. All right, so just a little bit of a preview of what's to come. So typically we would program these robots. They're vacuum cleaners. We use a vacuum cleaner called the Neato. I'm probably the foremost champion of the Neato vacuum cleaner in the entire world. Don't call them Roombas, they are Neatos. I will get mad at you if you call them Roombas, but not really. Of course, we don't have access to our physical Neatos. So what we've done is we've created a simulator of the Neato in a platform called Gazebo. So you'll be able to program the robot using all the same sort of techniques that we use in the class typically with the physical robots, but we'll be doing things in simulation. The simulator is actually pretty cool, and we can do actually a few fun things that we wouldn't be able to do with a physical robot. So looking forward to trying that out and seeing how it goes. All right, so all right, here we go. So what is a robot? So here's a couple of robots, probably pretty familiar with C3PO on the left. If you're somebody around my age, which none of you obviously are, you would remember this robot on the right, Johnny Five from the Short Circuit movies. Highly recommended, classic sort of 80s era robot movie if you're interested in checking it out. And in the beginning of this day document, we're going to have you sort of diving into defining what is a robot. All right. So we're going to give you three different definitions of what a robot is. And you can see what sort of devices or sort of machines would meet those various criteria. So one of them is a machine that looks like a human being and performs complex acts such as walking or talking. Otherwise, a device that automatically performs complicated, often repetitive tasks, or a mechanism guided by automatic controls. So these three definitions sort of give a different spin on what a robot is. Hopefully you'll get into some fun conversations at your table, or if you're doing this on your own, you'll have a good time thinking through what different types of machines or devices would fit these characteristics. Maybe we're robots too. That would be something to think about as well. All right, so I won't go over that exercise in a huge amount of detail. There's a couple examples of what you might put down for this exercise and the solutions. So if you're interested in checking those out, go ahead and do that. All right, so now that this is kind of a warm-up exercise, hopefully things are going well for you now. Now we're gonna sort of unpack a particular way of thinking about robots. So one of the things, in my view, that distinguishes robots and makes them super cool is that they interact with the physical world. So the physical world is hugely complex. It has all sorts of unpredictable elements in it. Just think about all the things that you sort of interact with on a day-to-day basis. I guess it's much less much less things in this current environment with everyone locked down to their houses, but Normally, as you go around, obviously, you're interacting with various people, various machines, various infrastructure of a city, or things of that nature. Um, Similarly, the sensory information that a robot takes in is very complex. So uh, imagine something like an image that a robot might have to process. A full 50% of our brain's cortex is actually devoted to sensory processing, and of that 50%, a large portion is devoted to visual processing. So there's a huge amount of computation necessary to make sense of the sort of sensory information that we take in. So that's another thing I think is super cool about robots, and something that we'll get to explore a little bit in this module as we dig into various types of sensors. All right, so for now, let's just think of a really simple robot. So let's think about a robot that looks like the following. So let me zoom in on this figure right here. All right, so this dashed line represents our robot. The input to it is some sensory data, so we call that S of T. So that could be, like I said, like an image. It could be a bump sensor. It could be all sorts of various things, a GPS, who knows. And there's some sort of thing in this box. We're not going to worry too much about what that is yet, but it's going to take that information and output a motor command. All right. And the motor command could be sort of a stand-in for anything that has the ability to influence the physical world, but a motor is probably the thing that we're most familiar thinking about when we talk about robots. So imagine it takes in some sort of sensory information. In this box right here, it decides what the correct motor output should be for that sensory information, and then it feeds that into the environment. Who knows what's going on in there, and then the environment does its thing, or something happens, physics happens, and then out of that comes a new sensory signal, and we have that sort of feedback loop. What's really cool about this, even though this is pretty simple, even though all we have here is just sensory information in, motor command out, there's no sort of like fancy sort of memory or stuff going on in here. We're just sort of mapping directly from sensing to motor. Because the environment is so complex, we can actually have some pretty cool behavior of a robot, even with this relatively simple structure. Okay, so we're going to start out with that really simple model of what a robot is, and we can see that it's actually pretty powerful. All right. So in this first exercise in this section, we're going to ask you all to think about what are some robots you could sort of design using this type of structure. Let's see, and I'll walk you through one in just a second.